Greetings. This is Graham Warren working with you on the AnyLogic simulation model for the Antico Caffe Greco case. So this is AnyLogic is a simulation tool that provides a number of different modeling alternatives. The one we're going to be interested in here is the process modeling or the discrete event simulation modeling functionality of AnyLogic. AnyLogic comes with a relatively steep learning curve, which we're going to support or try and work around by providing you with models for the two case studies that are relevant, where we're going to use AnyLogic. And we will support that, with the sync sessions and a workshop for those of you who are interested in maybe digging a little bit deeper into AnyLogic. So what I recommend is installing the AnyLogic tool. Let's see how we do that. We just go to AnyLogic.com, and there's some downloads here somewhere. Let me just see if I can find this. There it is, the downloads. Now you're going to have to register for the personal learning edition. I suggest using the your Hopkins email address to register. It's a free download. The professional version, is costly. AnyLogic was chosen because it's free and it provides Mac and Windows versions, maybe Linux version also, but Windows and Mac seems to cover most of our needs. Once you've got it downloaded and installed, you're going to, and I want to launch it as well. So let me just emphasize that. The way this seems to work best is go ahead and launch the personal edition, and then come back in and download the model. So let's just get it started. Takes a little while to launch. That's fine. So I strongly advise launching AnyLogic and then loading the file from your downloads rather than trying to download and then rely on a file association to load AnyLogic. It doesn't seem to work all that well. That way around, at least. Okay, still loading. Okay, so we're in, and what we want to do is just close this. So I guess, no, we're fine. It immediately bounced in. Now I actually have loaded this model, but I want to just show you, it may not be loaded in your case. So I'm going to go ahead and click on this. This lives on a Google Drive somewhere. Download it. Okay, I'm not getting the download option for some reason. Maybe it just knows that I'm, let me try that again. There it is. So let's download it. And I'm going to go into my downloads and then just upload it from there. So I go into AnyLogic. Let's close this out. Go into File, Open, and then in my downloads, you can see I've downloaded it several times here, but this is the one. And say discard all changes and reopen it. It's called ACG Spring 2024. Now, you may have other models in here, depending on what you've worked on before, but this is the Antico Caffe Greco model. So I want to do a quick walkthrough. What we're generating here are customers. Now, I'm looking at the base case, and I want to actually, I have a generic model here that can accommodate a number of cases by adjusting these simulation parameters. But let me just walk you through, what is going on here. I'm generating customer here with a rate that's specified down here, arrival rate. So those are generated according to a Poisson process. You can see that specifying the rate here, and it is the arrival rate that is connected to this block here. So whatever you set this arrival rate to, that is the Poisson arrival rate being used in your model. Right, so from there, we're going to start a timer because I'm interested in how long does it take from time of arrival to completion of their coffee. And that timer is implemented using these two blocks here, time measure start and then an associated time measure end, which references time measure start, so it knows where the timer started, and we're going to get a histogram of those times along with a mean here, and this is actually W sub S. So I see I've got it listed as W sub Q, but it really is W sub S. So let me go ahead and just change that because it's inaccurate. So there it is. And we'll go ahead and save. Right, so that's the time from time of arrival to completion of their service. From there, the customer grabs a barista. So we're seizing a barista from the pool of servers. Now, I've labeled them servers rather than baristas because if you do decide to automate, then the servers are robots or automatic, espresso makers as opposed to human baristas. And once you've got a barista, so they grab from the so-called resource pool here, the servers, and the number of servers is spelled out here, number of servers, and you can control that by adjusting that number here. So it could be in the base case just one, because we have 3 baristas, but they're each serving an independent arrival stream in the base case. And so you analyze each barista sort of in isolation, and in that system, there's one barista with an arrival rate of, I think, 26.4 per hour and a service rate of 41.1 per hour. And of course, the standard deviation depends on whether they're trained or not. Right, so once you've grabbed the barista, then we go to a delay here, and that delay is just the service to make the actual coffee. Now, there's a little bit of a twist here. And that is, we're certainly going to use a normal distribution. You can see there's the mean service time listed here and the standard deviation. And those two reference these 2 remaining parameters of our model. But there is a twist, as I said, and that is that this parameterization actually gives us a truncated normal distribution. So let me just lay out for you what's going on here. So in the base case, or any case where they're not trained, the mean time, I think, is something in the ballpark of, I want to say 87.6 seconds, with a standard deviation of 83 seconds. So this is standard deviation, and this is the mean. And I think you can quickly see that there's going to be significant probability mass to the left of 0. But these are times, right? Processing times, and we cannot tolerate negative times. If I sampled from this distribution, it's quite likely this is essentially 1 standard deviation below the mean. So we know that about 68% of the mass of a probable distribution lives within 1 standard deviation of the mean. That means 15% on in each tail. So this here is approximately 15%. So, and I just simply can't tolerate negative times. So what we're going to do is we're going to truncate it here. And our resulting distribution is just simply this. It's going to, let me try that again. It's going to go like this. I'm just chopping it off basically at 0. Now, if I sample from this distribution, I'm actually going to get a resulting mean and standard deviation. The standard deviation is going to be lower because my distribution is now less spread out, but my mean is going to be higher because I have a higher distribution. This chopped off distribution effectively has to be raised a little bit to accommodate the additional 15%. So there's some slippage here in situations like this. I'm going to not make an adjustment for the truncation. So that means that in situations where you have a high standard deviation, like in the base case, or in any situation where the baristas are untrained, that your estimates are going to be on the high side because the means are going to be higher, maybe the standard deviations are lower. So I'm not exactly sure how bad an approximation it's going to be, but it is an approximation relative to what you would actually get in real life. And that's just simply down to this issue of the normal distribution having some overlap over zero. So notice if you're in the trained setup that you're again sitting at 87.6, let's say, but your distribution is very much more peaked when you've done the training, because now the standard deviation is something like 8.3 seconds. So the probability of overlapping zero is really tiny now, because you're about 10 standard deviations. The center, the median of the distribution is about 10 standard deviations away from zero. So this overlap problem is negligible for the trained or an automated coffee shop, but it's relevant, if you have untrained baristas. So I just mentioned this nuance, and we're just going to ignore it and just take the results as an approximation. Right. So from there, we then release our barista. That just releases the barista, so they can go back to the pool, and then they're able to serve the next customer in the line, in their line, or in a pooled line, depending on how the setup looks. We stop the timer, and then we destroy the customer. Our statistics are going to include the line length of folks waiting for a barista, the utilization of the resource pool, and then also the distribution of the time in system as expressed in this distribution and given by a mean. So in the next clip, I'm going to start to analyze these different scenarios for you by adjusting these parameters.